who's an expert in oil and gas, working at that undisclosed company, but he has like 20 plus years of experience in the field. He's also just graduated in the Master in Numerical Methods, and he has a few masters, actually a few postgrads. And well, I will not tell much more than this. Okay, I just give you the floor. I just wanted to warn that this is an informal kind of meeting, so people are actually allowed to make you questions during the meeting in case there are.
And the floor is yours. Okay, good morning, everyone. So my name is Andino. So just briefly to introduce myself, I'm a petroleum engineer, and I've worked for 20 years in the industry. And Ricardo invited me to give this talk. And okay, so it's a talk for people who are outside of the oil industry to try to introduce it. But at the same time, I know the audience is extremely well qualified in numerical methods and math. So I tried to balance to give you like an introduction of what are the main challenges that we face in reservoir simulation in the oil industry. And yeah, basically give you a bird's eye view for just maybe spark your interest and tease you if you ever want to get involved in this fascinating industry. It's just some quick disclaimers before I begin. Everything I'm going to show you is in the public domain. There's nothing proprietary, nothing confidential, and all the opinions that I would express are my own and they don't reflect any of my employers. Okay, so very quickly, a presentation structure. I'm going to introduce reservoirs, the kind of physical processes that we model, and how we model them. I'm going to go a little bit into the math that is used to model reservoirs, and then I'm going to go into the big topic, which is what are the sources of error. And I'm going to go into constitutive laws, and something that might be very specific to the oil industry is that we're not very confident about the properties of the domains that we're modeling. So we do a lot of inverse modeling. And then I'm going to mention a couple more simulation topics that might be of interest. Okay, so first, what is a reservoir? A reservoir is a porous rock that bears oil or gas, and oil or gas have less density than the water. Remember, as if you drill a well downward, you will always find water. So all the porosity, all rocks are always porous, and they're always water bearing. I mean, after 5 or 6 meters, whatever the water table is wherever you are, you will immediately find water. And the water is, of course, much denser than any hydrocarbon. So whenever hydrocarbons are generated in the mother rock at high temperatures and pressures, they will float up through this porous medium. And occasionally, a very, 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 very small percentage of these hydrocarbons that are migrating up through geological times, they get trapped by some seal rock. You can see there's some variations, but it's normally like a structural anticline or some fault that generates a seal where it normally shouldn't be, or a salt diaper that deforms and causes a structural trap. Okay, so there's 5 types of fluids. You might be familiar with gas and with oil. There's actually a lot in between. What we call gas is actually dry gas. And dry gas is basically only a vapor phase, both in the reservoir and at surface conditions. However, all the other gases, such as wet gas and gas condensate, they turn two-phase. So basically, gas condensate has this, it's called retrograde behavior. So you actually depressurize the reservoir and liquid drops out of it. It's kind of strange. You would expect that as you depressurize, right? So it becomes two-phase. It's a rather counterintuitive behavior. And then you have the classical black oil, which is basically defined by being low shrinkage. So as you lower the pressure, some gas comes out of it, but not too much. And high shrinkage oils or high volatile oils are oils that when you deplete them, they shrink by a lot. So this is a grosso modo, these are the fluids that we have. So what kind of processes do we model? Which essentially three basic processes, the three categories of basic processes. There's a family within each one. The first one, we call it primary depletion. And the idea here is you drill a well to reach your reservoir. And basically, when you're drilling a well, this is a very important concept. You have to, at all times, we call it the well must be dead, right? So you cannot let fluids from the formation into the well because you have a blowout. And these are like these, newsworthy events. So when you drill a well, you have this mud weight, this mud column that's basically keeping the pressure inside the well higher than any layer cake formation that you're touching, right? So once you lower your casing, you cement your well, you perforate exactly only what you want to allow to produce. You can remove the hydrostatic column from the well using pumps or other methods. That's a whole topic. And basically, you lower the pressure on this well, which behaves like a pressure sink, and your fluids, which are at high pressure, they start moving towards your wellbore. Okay, if that's all you do in the reservoir, that's called depletion, right? You might get some help. Normally, like the single phase expansion of oil will only recover 3% of the volume, depending on the conditions, right? But you might get lucky and have a gas cap on top, and the gas cap it behaves like a gas, right? So you double you lower the pressure to half, the volume will expand by 2x, right? So if you drill your wells in the low portions, the gas cap might give you extra energy, and your pressure doesn't get lost so much. Or you might have an active regional aquifer that helps you bring the oil into your producer wells. But in general, no field gets abandoned. As a general rule, most fields, they don't just have primary depletion. What happens is you're producing your oil and the pressure starts to drop. That means the rate that you can get out of the well, since you're running it at constant bottom hole pressure, it gets lower, and you start what's called a water flooding process. And what does the water flooding mean? Is you will inject water. So some of these wells, you will drill them specifically for the purpose of injecting, and you will use this water that you inject for two purposes: to keep the reservoir pressure high and to sweep the oil from the producers to the injectors. Normally, you can get recoveries of the oil in place, originally in place, with depletion between 1 and perhaps 5%. If you're lucky and you have an active aquifer or gas cap, you might get 25 to 30%. With water flooding, you can get recoveries between 60, well, between whatever, it could go lower, but say 30 to 70% of the oil in place. And finally, enhanced oil recovery. This is a big bag it's a big category. So it's all the things that you do when your field is very mature and you're producing a lot of water from your producer wells. Things that target, like for instance, polymers. You try to increase the viscosity of the water. CO2 injection. You try to reduce the interfacial tension between the water and the oil. There's a lot of surfactants also. There's a lot of processes that you can introduce. This is when you have a very mature field. Normally, this is very expensive, and sometimes it's not even economic to do. Most of the fields, oil fields, are in water flood. Okay, so what do we use these models for? There's so many uses. The first one, which is what my specialization, is development optimization. So you have this oil field that has been discovered. There are perhaps 3 exploration wells, 10 appraisal wells, and you have to make a business development. So how many wells are we going to put in this field? Will they be vertical? Will they be horizontal? Will they be multilaterals? Where should I place them? Shall I target a specific formation? Shall I stay away from the aquifer because I expect the aquifer will be strong, or shall I stay away from the top because I expect the gas cap to develop? So all these questions you have to address, and for that, simulation models are the perfect tool. So development optimization or reservoir management. And the second one is to determine reserves. And reserves, you don't determine reserves with a model. There's much more to reserves than the simulation model, but simulation models provide you with reliable forecasts. Reserves involve a lot more things, essentially because you have to look at license periods, whether the economics are changing over time. You have to have a price forecast. You have to look at existing technologies. There has to be an approved development project and a commitment to invest, etc. So reserves are much more than just simulator output, but the output is normally, it comes from a simulator. So it allows you to, reserves basically are the value of a company. How much oil will this company be able to produce? Okay, so maybe a little bit to what you guys might be more, some stuff that's more up your alley. What's in a reservoir model? So in a reservoir model has multiple components. I'm simplifying a little bit here, but essentially we have a geological model. And the geological model is what you would call the grid. And that contains all the subsurface. It's like an integration of all the subsurface information that we have. And it contains the basic geometry and the porosity and permeability. I haven't defined those terms. I will do that later. But porosity is essentially the empty space inside the porous medium. And permeability is basically what is the penalty and pressure that you will pay if you try to push a fluid through that porous medium, right? It's not free, it doesn't flow automatically. You have to push it, and there's a penalty in terms of pressure or energy. Then there's a flow model, and essentially we're solving these flow equations. This is a simplified case called the black oil model, but it's essentially a material balance. And in order to determine the velocities, we use what's called Darcy's law. I'll get into that. There's a well model, and the well model it's below grid resolution, right? So it's it's a sink and a boundary condition, and the well model basically sets the boundary conditions, or you can treat them as sinks or boundary conditions. Let's think of them as sinks and sources in your 3D domain, right? They set the boundary conditions or the sinks and sources for the simulation model. And then you could have some models have a facilities model, which control the wells to basically forecast correctly the future conditions. Okay, an important factor to consider is this is a multi-scale phenomenon. So you have on the left, this is four scale simulation. No one in the industry does that. You cannot model a field. A field is maybe tens of kilometers and hundreds of meters in height. A reservoir, so you cannot model that explicitly. So we live at a completely different scale. Like your average simulator will have cell sizes in the order of maybe vertically something in the order of 50 centimeters to 1 meter, and horizontally maybe 50 to 100 meters. So these cells are quite coarse because we need to model a huge volume. Yeah, so of course we do continuum assumptions, right? So we cannot solve Navier-Stokes on the porosity. We actually don't know exactly what the porosity looks like anyways. So we have to make a continuum assumption, and we use some functional approximations to describe this complex porous process, which are subject of discussion in the next slides. Okay, some critical concepts of flow and porous media. So you have a certain porosity. As I mentioned, all rocks have porosity. All sedimentary rocks particularly have porosity, and you can have 2 or 3 phases, and these phases are immiscible. That means that basically the oil and the water and the gas, even on the same cell, they will have different pressures. Why? Because the oil sort of tends to be non-wetting. Actually, it doesn't touch the pore wall, and there's a certain curvature in the droplets of oil, right? And this curvature, this tension, is sort of compressing the oil. So the oil porosity, the oil pressure is actually higher. So you have to segregate the pressures of the different phases, right? So we have mass conservation for every phase, and we have Darcy's law, and Darcy's law is actually derived by some averaging and neglecting terms from the Navier-Stokes equations. And it essentially, Darcy's law essentially tells you, it's a bit like Fourier's law of heat transfer, or Fick's law. It tells you velocity is proportional to the gradient of a potential. Sorry, I forgot to mention. On the left there, this is called a relative permeability, and that models basically as a function of the saturation of the different fluids, how much they tend to flow. So if you have a lot of water and very little oil, the water will tend to flow preferentially. That would be on this side. Oh, you can't see my cursor. And on the other hand, on the left hand of the plot, if you have mostly oil, the phase that will flow will be predominantly oil. So basically, the flow is proportional to the volume. Okay, so a little word on the reservoir fluids. Basically, what the simulators are calculating internally, they're using equations of state, and these equations of state basically require input from a detailed compositional characterization. So you run your representative sample through a chromatographer, and out the other end, you burn it, and you get a signal on a capacitor, and you get these peaks, and these peaks tell you what's inside your oil. And every oil is different. It's like people. Every oil is different. You could have hundreds of pure chemical species inside each oil. Right, so and this compositional input is sort of upscaled in many ways, and it's used in order to determine the parameters of the equation of state, and you use that in order to calculate vapor-liquid equilibriums and to determine the properties of your phases, of viscosity, porosity, etc. These are the black oil equations. They may look scary, but it's actually quite simple. This is just mass conservation written for the three phases for oil and gas, and considering the fact that oil and gas are sort of dissolving into each other, but water is immiscible. So the water equation, which is the third one in the conservation, that is a simpler equation, right? And we have our Darcy equations and a linkage equation, which says that some of the saturations has to be equal to 1. And then we have a lot of lab data where all the coefficients of these PDEs basically are functions of the solution. But we read it from tables. We don't use the EOS for this simplified approach. And then we have what's called the compositional approach. And the compositional approach is more involved because now instead of tracking oil, water, and gas, we are actually tracking the detailed components inside each of these phases. And it's basically the same set of equations. You have a mass conservation per component. You have a mass conservation for the water specifically. You have 3 Darcy laws for each phase. You have linkage equations, same as before. You have the saturations add up to 1, but also the molar fractions have to add up to 1 in each phase. And then you have the phase equilibrium, which is calculated from the equation of state, which is what I showed you before. Most formulations end up with, after you do all the substitutions, it's NC is the number of components, right? So the total system is 2 times NC plus 18, but what you can reduce that by substitution to a number of components plus 3. And there's multiple ways to do that, and there's discussion about which one is more efficient actually. But I'm not going to go into that. Sorry, that animation is not working well. Essentially, all the simulators that we use, and the reason will become clear later, are finite volumes. Why? Because we don't need high accuracy because we're not sure about the properties of our domain. And it basically, another advantage is it allows for flexible gridding. I will show you some geological models. We need to have some flexibility with our gridding. And for time integration, there are multiple approaches. There's fully implicit, which is the approach of some simulators, but most simulators are actually sequential. And you split the variables to do the update. Remember, the coefficients of your system are dependent on the solution. So you solve the pressure implicitly, and then you explicitly solve the saturations. And what you see on the right, this is like it's a simplified problem. It's not the full complexity of the problem, but it's a two-phase incompressible flow equations. And basically, it's two separate problems. And this is the origin of the approach. You have the pressure equation, which is parabolic, but it's almost elliptic. So you're essentially solving the Laplace equation roughly for the pressure. And that is done implicitly. And explicitly, you solve the convection problem of the saturation. So the water propagating inside, that is normally solved explicitly. There are other approaches, somewhat one in between, which I really like, which is called adaptive implicit, which tracks where the saturation is changing significantly. And only those are solved implicitly. The rest is solved explicitly for the saturation. And as I mentioned, we have to do the coefficients of your system are highly dependent on the solution, so you have to do Newton-Raphson iteration. So commercial simulators are very pricey because we have few users, and there's this perception that the oil industry is pretty wealthy. So are there any open source alternatives if you guys want to get your hands dirty? Yes, the answer is yes, and this didn't exist for the most part when I started off. Only Boast existed, which is finite difference and pretty aged, I would say. But you have MRST, which is developed by Andreas Lier, Knut Lier from the University of Norwegian Technical University, and it's excellent. It's based on MATLAB, and his main focus was to look at unstructured grids. So it's got a lot of gridding functionality. Open Porous Media, which is an initiative, an open source initiative by many oil companies. The code is fully available in Fortran. You can download, and they also have both toy problems, but also open source reservoirs that you can use to tinker. And then OpenGoSim, which is the new kid in the block, which is the only one that has full compositional simulation. And it's actually marketed as a CO2 injection simulator, but it's a full-blown compositional simulator, so you can use it for modeling your oil fields. Okay, before we get into the main sources of errors or the main challenges that we face, this I wanted to share with you. Maybe someone will be helped by this sometime, because they're hardened lessons from using simulators for a long time. The first one is whenever you're going to sit down to use your simulator, you have to have a very clear objective. I'm going to solve this problem, and this is the business point. And the point is you have to know when to stop, because you can spend time and time and time, and if you're, it could be a random walk. So does the simulation that I'm doing serve the purpose that I'm trying to fulfill? And for that, you need to write down what exactly are you trying to solve. Second one is, do you really need to use a simulator to solve it? And that's a question you always have to ask yourself. Is there an analytical solution? And as it happens quite often, is there a database supervised model that I can use to solve this problem? That sometimes is the case, at least in the oil industry, right? Now, if you decide to do simulation, make sure you understand the physics. You should have an expectation of what you're going to get. And if that expectation is not met, make sure A, there are no errors, and B, make sure you recalibrate your perception, because it's what you understand that is guiding the whole process, right? And this is kind of silly, but strict version control, whatever. So we deal with a lot of input, and you need to control exactly what you're putting in, because otherwise you get funny results. And just change one variable at a time when you're doing research, because if you change 2 or 3, you never know what is causing the results that you're getting. So maybe basic stuff, but important to bear in mind. So what are the sources of error in practical simulation? Okay, so classically you will see this this chart in simulation books where you have a physical system, you idealize with your constitutive models and your conservation laws, and you get a mathematical model, you discretize that mathematical model, and you come up with a discrete solution. And I've added there the domain properties, because domain properties are, as we will see, a big source of error, right? So we model the physical system by assigning domain properties to it. maybe in mechanics you don't think about that because you know the properties of fluid and of steel. But in the case of reservoirs, you struggle a lot to determine your domain properties. So just one slide on discretization and solution error. So normally this is handled quite well, and it's not a big issue. For discretization, what you do is you test different grid resolutions. And you basically you try a notional development plan of what you plan to do on that particular field or reservoir, and you assess the impact of the grid in your outcome, your business outcome. And once, you will very quickly see that you get convergence. So you basically stop at the resolution. We don't have high order methods, so it's always the grid that you test for convergence. It's always H convergence, never P convergence. And the solution error, as I mentioned, the PDEs that we arrive at with Reservoir Simulation, they're highly nonlinear. So all the simulators have Newton-Raphson, and this is a lot of the focus in the simulator development, is how to update these coefficients efficiently. And you have tolerances and max number of variations, etc., that you can set. In general, commercial simulators are very robust, and you just use defaults, right? So my take on this is of course the topic that you need to address. But as a general rule, it's not at all the dominant factor in the uncertainty of our forecasts, and you can quite easily deal with this. So this is the discretization solution. I'm not going back to that. I'm going to talk a little bit about constitutive laws. So one of the constitutive laws I mentioned is Darcy's law. And Darcy's law says basically the rates. This is the rate per unit of cross-sectional area. It's not the velocity of any particular fluid. That's a bit of a misnomer. It's not a velocity. It's rate per unit of area because you have rock, and that rock changes your cross-sectional area. The actual velocity is faster. You have to divide by the porosity here to obtain the actual velocity of the fluid. But it says the rate per unit of area is proportional to the pressure gradient. And it turns out this is valid only at low Reynolds numbers or at low velocities. And if the experimental data shows that as you increase the Reynolds number, and this occurs in most fields near the wellbore, because your cross-sectional area to that flow is getting smaller and smaller as you approach the well, then you get a turbulence term, a quadratic term on the velocity, right? So nobody uses Horkheimer's law, and I don't know that there are any discretizations. We use very coarse approximations for the cells that contain wells. I'll get into those later. And another effect I did not mention, but we always assume that because these processes are slow, they're isothermic. And the formation is able to heat up the fluids as we depressurize gas, for instance. Because of the Joule-Thomson effect, the gas will tend to cool, but we always assume that is isothermal because that process is slow, but particularly near the wellbore, that's not the case. And you could, in certain regions in Siberia, you have hydrates forming in the near wellbore area because of this cooling of the formation, because of the rapid depressurization of the gas. Yes?
I just have a curiosity. In the vicinity of the bore, of the water, how fast is the velocity in reality in the pores? Just a curiosity, okay?
I never sat down to calculate it, actually. I can tell you it's the fastest by far, but let's say on a vertical, I mean, I would have to do some math. It's simple math, but I would have to.
Yeah, but because I was just thinking that if the Reynolds number, you're telling that the Reynolds number is greater than 10 on small pores.
Yeah, but the problem is not that the velocity is big. The problem is that the diameter is the order of microns.
Yeah, correct. So to have a high Reynolds number,
you need a very high velocity.
You need a very high velocity. That's why I was asking. Okay, never mind.
I haven't worked this out. Yeah, it's a valid question. I will look into it. I mean, this is something that's normally presented as, oh, dark sea flow doesn't work, but we never actually explicitly model the near wellbore area. We use approximations. Another constitutive law has to do with hysteresis. And here I hope to give you an intuition about why we have hysteresis in reservoirs. And here you have like this is a porous rock, and you have in the scenario in the top left basically you are at high capillary pressure, so the oil doesn't want to wet the surface of the pore, but it is able to go deep into small pores because it's at high pressure, right? So when you water flood this, what happens is you get droplets of oil remaining both in the large pores and in the small pores. Instead, if the oil was not at high pressure originally, then when you water flood and you recede and you get this snap-off effect and there's a droplet remaining, then the oil that remains is smaller, right? So it's the same rock, same process for water flooding, but because the starting point is different, right? And if you have cycles, and these cycles occur in certain occasions, then this leads to, you have to use models to basically take into account this hysteresis process. And we have hysteresis in two things, in what I call the relative permeabilities, which describe how the phases affect the flow of each other, and the capillary pressure curves. Kind of a long topic. Another source of error in the constitutive laws is the fractures. Some reservoirs, most reservoirs are actually fractured, but some are so fractured that we actually have to bother to model them as fractured. And the models that we have assume that the actual fracture network, which is very complex in geometry, is a bunch of sugar cubes. And we have some analytical equations that regulate the transfer of fluids between the sugar cubes and the flow that is occurring in the fractures. And as we have with elasticity models, none of them is perfect, right? You can use one particular model for a certain circumstance and another model, right? So these models, they have steady state assumptions that may not entirely be valid. So I don't want to go into fluid properties because that's a whole kind of worms. But essentially, we have constitutive laws that are mostly related to the fact that we are modeling at a scale which is not the scale of the true process. The true process happens at pore scale. These constitutive laws, they are very complex. They are very simple approximations of a very complex phenomenon occurring at pore scale. And as such, they have to make a lot of simplifying assumptions and therefore have a limited validity. Okay, now I'm going to go into input error, and just to give you an overview of the kind of data that we are having to integrate. We have data from different scales, right? So we have logs, for instance. Logs are measurements of physical properties that you obtain when you drill a well. You run these tools, they're called logging tools, and you measure resistivity, you measure speed of sound, you measure neutron absorption, you measure natural radiation from the shales. And you get all these logs, and these logs get converted to the stuff that we're interested in, which is porosity, permeability, and saturation. You have seismic data, and seismic data is 3D. And this comes from either generating vibrations or explosions on the surface, and basically setting up huge arrays of seismographers or microphones, if you will, and listening to the waves that come back, right? And then with all this information, you're able to construct a 3D model of everything that is underneath you. It's very coarse, very, very coarse, because only very low frequency can propagate in this universe. Then we have core data. So when we drill wells, we obtain rock samples. You have fluid samples. You have thin sections, which are obtained from core data, and they allow us to determine what type of pore structures we have. And finally, we have production data, right? And production data is a time series, and it's the response that our model should replicate, right? So our model should take all these inputs all around, right? We have to integrate it into a geological model, a flow model, a well model, and we have to be able to replicate the production data that we observe. Okay. So I mentioned the components of a simulation model. First one was a geological model. Okay, geological models, there's some order in the geological models. We have the seismic to guide our understanding of the geological model, and we have what are called our understanding of the sedimentary environment. Okay, when the reservoir rocks were set, we have some idea of what the setting was. Was it dunes? Was it a fluvial system like the one we observe here? Was it? There's many different types of sedimentary environment, and that constrains the things that we should expect to see. In a fluvial system, you expect to see, for instance, braided channels. But bottom line is, regardless of your understanding of the sedimentary environment, you have only a few vertical well penetrations, and as you see in this picture from Mark Bentley, you never know what's going on in between. You really never know. For instance, in this case, you can tell that if I'm flooding from the left and I'm trying to get a pressure response on the other side, the yellow is the permeable, and the brown is the tight rock, the shaded bed. You can see if the true scenario is the one underneath, you will get one response, and if the true scenario is the one above, then you will get no response on the other side, right? Because they're isolated hydraulically. So the geological models, they constrain what we can and cannot see, but bottom line is we really don't know what the properties are. A good geologist will generate realizations that are very reasonable, but you have to test these realizations to see if you are able to reproduce the observed behavior, the production curves that you see. Okay, so it's a bit of an inverse problem. You might be familiar with computer tomography, right? You have a source, and this source emits whatever it is. I don't know the physics of it, but you have an array of sensors, and as the array of as this goes around your head, you get this basically absorption versus the angle, and from that image, you're able to make an inverse model and obtain what is the cross section of that part of your body that is being scanned, right? So this is exactly the same. You have your production curves, and you have to figure out what are the domain properties that generate that production curve, right? So it's an inverse problem, which is constrained because we have some data, but we have very, very limited data. Okay, so how do we solve this inverse problem? There are many approaches. This is the old school low-tech approach, right? We think of model tuning as an artistic process, if you will. So what you do is you get your geological model, and then you start noticing that there's some mismatch between the forecasted production in a few wells versus what is actual. So you increase the permeability here, you increase the porosity, you lower the structure, and you go into an exercise of local adjustments. And this is a lengthy process, and it's very intense because as humans, our attention, is singular. So we focus on one aspect at a time. So it's a sequential process, and you come up with something that doesn't look geological at the end, right? So you can see here, this is a permeability field after history matching. That's what this calibration process is called, and you can see patches. We should expect more continuous variations, and that's not what we get. But this is the old school approach, and to some extent it works, but it's got its risk, and the risk is overfitting, right? So this is again open source data. You see here a very nicely on the left, a very nicely history matched model, and this happens quite often. You come a few years later, you update the production history, and you compare to the forecast, and they deviate significantly. Okay, so clearly you see here on the bottom right, the water cuts that the model is predicting has a completely different evolution from what actually happened, and this is because the way you reproduce that water cut is not the way the true mechanism that is going on in the reservoir. So even if you have a perfect history match, you don't know whether you are overfitting or you are actually predicting correctly or capturing the signal basically, as opposed to the noise, right? So I advocate the need for rigorous testing, and here I follow a bit in data science because we don't have physics. You have to be very rigorous in the way you test, right? Because it's all you have. If you don't have good testing, you cannot say, I am using these time-tested laws. No, you're just doing some high-dimensional circles. So the way time series problems get tested in data science is you reserve the last portion of your data set and you predict it blindly. Okay? Here I'm showing cross-validation, but the testing is the same principle. So your testing or validation set should be in the past, and you should blindly forecast the future, right? So the part of the problem, and you have to understand, is maybe a simulation run will take 1 day, and it's very laborsome to just generate something that works. It's a lot of work with the tools that we have. So this is why sometimes it's only done once, and just to comply with the fact that you have to reproduce a history. But the focus on prediction is sometimes lost. There are alternative approaches, and this one I really like. I haven't applied this myself, but I know some colleagues that do. And this is treated as an optimization problem. So, and here you need a very good geologist that will generate for you a lot of geological models. And what you do is you take this diverse geologic dictionary, which is a lot of possible realizations that are compatible with the observations that we have in the well and the seismic, but they're very different. They're qualitatively very different. The more different, the better. It's not an orthogonal based like we would like, but you want them to be as different as possible. And then you treat this as an optimization problem. So you basically take a linear combination of these models, okay, and you make a new model out of them. And then you run your flow simulation and you make a prediction. And then you have a mismatch function, like a loss function. And then you try again, and okay, now you assign different for your new coefficients. You assign different coefficients, and basically you can use some sort of gradient method to minimize the discrepancy between your prediction and the observed data. And this is one of the approaches. Another approach, which I'm very keen on, especially for fields where we have limited data, is to use multiple deterministic models. And that is, you sit down with your geologist and he says, okay, we could have long channels that connect, long channels that don't connect. We could have point bars. We could have blah, 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 many different realizations of how the geologist thinks about this model. And basically you do a classical history match on each one of these models, but they're all different. The qualitative are different, okay? And this will give you intrinsically different forecasts. Here you have a curve of recovery versus time. And each one of these scenarios will give you a different assessment of what the field performance should be. And it's normally applied in green fields, which means fields where we have very limited data. Maybe we have a few production tests, but we don't have production history. And I think it's a great approach because it avoids, it conveys uncertainty to your management, the true uncertainty that we have, and it avoids anchoring bias. We shouldn't think about these reservoirs as being known. We really we will only know. I mean, some uncertainty will remain, but we will only know once we produce the last drop of oil. So especially when we have limited information, we should have like very, very different model designs. And this is an approach which I'm very keen on, and it's to do a stochastic inversion. So what you do is you use for any input that is scalar, for instance, the level of your water, or you could use a porosity multiplier. You use a distribution, and you normally just use in your prior model here on the top right. You normally would use like a uniform distribution, and for other properties, array properties, you use discrete realizations, and the more different, the better. And what you do is you run hundreds of combinations of these parameters using Monte Carlo, and yeah, with certain sampling details that are not relevant right now, and you obtain basically a lot of production forecasts. And you're able to say, okay, of these hundreds of production forecasts, there are a few that are within a tolerance of what I observe in the field, right? So that allows you to come up with posterior models that are constrained. So it's like a Bayesian update. So you have an initial distribution, which is very silly. It's just a uniform distribution. And through this loop, you generate a lot of stochastic runs, and you're able to come up with a posterior distribution that is updated, that gives you a constrained set of runs, right? And you're able to forecast into the future with the proper uncertainty that you observe, because you're forecasting with an ensemble. You're not forecasting with a simple realization. And I wonder, and this is an open question, whether you need to do testing here, or you are just the fact that you're matching, you're constantly forward predicting and matching the historical production is enough. Computationally, this is very intensive. So if you want to apply this on a big field, good luck to you. You need models that run in minutes, not hours. Okay, and this is also like the common sense remarks that I made at the beginning of the talk. Always do parameter screening if you're looking at uncertainty, because there might be things that are not affecting your target. So if you want to look at the recovery of a particular field, maybe there are certain parameters that are not relevant for you to look at because you try them in the whole range. Let's say you don't know what your oil viscosity is exactly. It might be 0.8 centipois, it might be 1.2 centipois. If you do a run with 0.8 and a run with 1.2 and you get exactly the same results, you don't know, but it's not relevant. Okay, but there are other parameters that are different. In this case, for instance, the Rossard volume multiplier. Okay, so if the size of your field is larger or smaller, it gives you a completely different forecast. Okay, then you need to really focus on that.
Sure. What about shape? Because
Yeah. Okay, so I don't want to get into a lot of detail. What normally happens is the geological model process is manual. 99% of the time it's manual, and you generate a grid, and you can do grid resolution sensitivities, but to change the grid is very laborsome. So what you do is, let's say you want to account for the fact that it might be slightly thicker or slightly thinner outside of well control. In well-controlled areas, well, areas where you have wells, you know, but outside of well control, you don't know. So what you do is you define an array property which measures the distance from a place where you know the pore volume, and you essentially multiply the pore volume of those cells that are far away from the wells by 0.95 or 1.05 stochastically. So that is easier to do. There's a new school which they call it the big loop. So if you are able to automate the whole process of generating your geological model and running it and getting some evaluation of your loss function, and then based on that, but this is experimental. But
yeah,
the grid is fixed for practical purposes.
Another chart, how big is uncertainty, like the outer loop uncertainty?
It depends on the specific fields, because, like, for instance, in a shale system, everything is permeability. So I mean, shale, you must have heard that there's like whatever hundreds of years of shale oil for us to use if that's what we choose to do. So it's huge. But the problem is you drill your well, you frack it, and you're only able to drain a small volume around your well. So the volume is irrelevant. It's the permeability. Can you enhance the permeability through the hydraulic fracturing process? So on other systems, if you have, say, a volumetric gas cap or a gas field, yeah, volume is everything. So it depends on the system. Like, this is a bit like psychology, like every person is different, like every reservoir is different. Right? You have some principles that you can follow.
But to the point that in some wells you need some techniques and in others you need.
No. You always apply a uniform simulation method, but you have to basically, depending on the type of reservoir that you're looking at, it's a very healthy exercise to do in general. If you're considering uncertainty, even just to know what knobs to. Let's say you're doing a deterministic history match in the classical sense, and the approach zero that I called it. This is still a useful thing because you know what knobs you will need to adjust in order to get the different results. I don't know whether I addressed the question.
Yes.
We can take it after.
But I mean, this comes up in every numerical problem that you're facing.
What I think differentiates the oil industry from the others is the domain properties are very uncertain, very uncertain. Okay, and that's to wrap up that part of the talk. So highly detailed models cannot overcome the underlying absence of information, right? So this is why we use finite volumes and we use relatively coarse cells, because we don't really know the domain properties. And also they can have the negative effect of creating a false sense of understanding. This is why stochastic methods are, in my view, much more superior, because you're able to forecast an ensemble, and this ensemble shows you the uncertainty. So you are approximately right. You know the truth should be in close to one of your runs, but that's better than to deterministically say, oh, we're going to recover XXXXX barrels. And you're exactly wrong if you do that, right? So some other challenges. How are we doing for time? We're close to the end. One of them is well coupling, and this comes apropos of what Ricardo mentioned. What you have this graph on the bottom right. This is the pressure distribution inside a cell that contains a well, and because the cross-sectional area goes with 1/R. So as you're approaching your well, your velocity becomes really large. And I didn't do the math for Ricardo, unfortunately, but your velocity becomes really large, right? So and basically it's below, everything that happens there is below grid resolution. So what do we do is we use steady state models that they tell us, okay, what is the rate that you're going to get for each phase out of this well, based on the pressure of the well and the average pressure inside the cell. Okay, so again, like with relative permeabilities, we are modeling a very complex microscopic process. Here, with a large cell, we're modeling something that you can see that's huge pressure variations. You should model that explicitly. We just use these simple equations that tell you, okay, what is the rate that you're getting out of your well as a function of the average cell pressure, which is what the simulator gives you, and the bottom hole pressure that you are prescribing. Okay, so you can mitigate this with local grid refinements, but you have to basically decide whether this is an issue in your model in particular or not. In general, well treatment is and the well model is in itself a whole 1-hour presentation of this. Another challenge that we face quite often is the issue of initialization. We think of these reservoirs as being static, and okay, if you look at the interface between the air and the water in a water tank, it's going to be flat, right? But here you have many factors that might change that. For instance, you could have an oil reservoir. The oil has migrated, then during some geological epoch, some water chemistry changes. It creates a seal, and then there's a deformation, and then all of a sudden you have a tilted contact. Or like shown here, you have hydrodynamics that are causing your oil water contact to tilt. And in those cases, okay, you have to decide whether you're going to try to calculate, try to equilibrate these. Like basically, if you equilibrate, you get flows from the beginning, or if you force, then you have to fudge your constitutive equations so that so it remains static. So this is it's a bit lengthy to explain essentially, but it's a challenge. So how do you set initial conditions that represent the physics of what is going on down in the reservoir when you have tilted contacts? It's a big problem because it is steady in the reservoir, but the physics dictates that it shouldn't be steady. So how do you do that? And finally, and this is the last slide, this is not a challenge of simulation, but a challenge in general that we face is we have to do, once you have your model and you trust it, you have to do optimization. So you need to decide how many wells, where are you going to place them, how are you going to time them. Will you drill a lot of wells at the beginning? Will you phase your wells, drill them slowly and sort of build up as you need? Will it be vertical wells? Will it be horizontal? So all these decisions, that's what we build the models for, basically, is to test all these decisions to come up with an optimal strategy. It's common to do what's called multi-targeted optimization, where you're looking at recovery, but you're looking at economic parameters. And you want to find basically solutions that are on this Pareto frontier. You want basically for the ones that are inside the frontier, you can either increase, for instance, for that one labeled B, you can either increase your recovery at the same net present value or get a better net present value at the same recovery. So they're called dominated solutions. So like how to come up with good development strategies, and especially if you can do that somehow automatically using reinforcement learning. That is a hot topic for a PhD thesis, by the way. That is one of the challenges that we face in the industry. And that was my last slide, but I'll give you some references for study if you wish to dive into these topics. These are chosen to be like good initiation books. I particularly recommend this talk by Andreas New from the University of Norway. And Mark Bentley's reservoir model design is excellent. It's a very simple read, actually. And computational methods for flow and porous media by chain is an excellent overview of the different numerical methodologies. With that, my talk concludes. If you have any further questions or things you want to discuss. Support guides are gone, so share. Okay. Okay, guys, for those of you who are online, do you have any questions or?
Is there anybody online?
I'm not sure the speaker is enabled.
Check out the chat also for those who read.
No question. Okay.
I have a question.
Okay, sure. So I'll just stop recording.